Welcome to the last section in Chapter 10. We're going to be doing some probability using geometry. We're going to be using segment and area models to find the probability of certain events happening. The main formula we're going to be using here for probability is right here. We're going to take the number of favorable outcomes over the number of possible outcomes that could happen. So what we want to happen over what could happen. Okay, so with that being said, we can write this as a fraction or as a percentage, and when we do that, the fraction, the top number, the want, should never be bigger than the bottom or what could happen, because so what we want to happen can never happen more than what could happen. In percentages, we can never have more than 100%. There's never going to be a time when there's over 100% chance of something happening. So when we're using probability in terms of length, okay, so we've got an example up here. Point S is on line AD. It's chosen at random. The probability that S is on BC is the ratio of the length of BC to the length of AD. So if we want to know what's the probability that lands on BC, we take the length of BC and we put it over the length of the whole segment AD. So our example problem here is if we've got the point P is chosen at random on line FJ, what's the probability that P is on GH? So if we take the distance of what we want to happen, G is here at 6, H is at 11, giving us a distance of 5. And then on the bottom, we put the distance of where it could be, so from F all the way to J. F is at 4, J is at 15. Giving me a distance of 11. So the probability that a point is chosen on GH is 5 out of 11. Our next example, we have a commuter train that runs every 25 minutes. So if I draw this as a number line here, we've got the first departure at 0, the second departure 25 minutes later. We've got a commuter that arrives at a station at a random time. What is the probability that they will have to wait at least 10 minutes for the train? Okay, so if we did 10 minutes shorter than the 25, this is the amount of time we want them to wait at least, which would put it at about 15 minutes. Well, if we want it to be at least 10 minutes, we're looking for this distance here. Well, from 0 to 15, that has a distance of 15. And then the total distance from 0 to 25 is going to be 25. So we've got 15 over 25. Now once we find the probability, we have to reduce it if we can. Well, 15 over 25, I can take a 5 out of both. And that simplifies down to 3/5. So the probability that they have to wait at least 10 minutes is 3 out of 5. The next example, we've got a river ferry runs every 40 minutes. So again, I bring my number line here. I've got the departure at 0, and then the next departure 40 minutes later. If a passenger arrives at a ferry station at a random time, what is the probability that he will have to wait no more than 25 minutes? So 25-minute wait, which would put us over here till about right there. Okay, if we want it to be somewhere in this area. We want it to be less than 25. Well, 25 minutes less than 40 is right here at 15. So we want that 25 on top. That's the part where we're looking for. And then the total again, 0 to 40 is going to be 40. So now again, I simplify this down. I can take a 5 out of both. I'd be left with 5 over 8. Our last example, a stoplight at an intersection stays red for 30 seconds, green for 15 seconds, and then yellow for 10 seconds. So if I start here at 0 and I want 30 seconds for red, and then it's green for 15 seconds, so that would bring us up to 45 seconds, and then yellow for 10 seconds, which would put us at 55. Okay, this is what our number line would look like. So now when they want the probability that you will arrive at a green light, well, green is in this group right here, between 30 and 45. That is a distance of 15. On the bottom goes the total. I've got from 0 all the way to 55 here, so it'll be 15 over 55. Again, I need to simplify that down if I can. I can take a 5 out of both, giving me the probability that I arrive at a green light is 3 out of 11. When we're talking in terms of probability in area, okay, we're going to use that same formula, the favorable over total, but now we're going to be talking about in terms of area. So I want the area of what I want on the top and the total area on the bottom. So again, want over total. Okay, so for example, this first problem, a circle is inscribed in a square. A point N in the square is chosen at random. What is the probability that N lies in the shaded region? Okay, so I'm only looking for this area outside here. And now we've done this before. To find that area, we can take the area of the outside shape, which is a square, with a side of 5, so that would be 5 squared is just 25, and the area of the circle inside. Now, the circle has a diameter of 5. To find the area, we do pi times r squared, so pi times 2.5, which gives me an area of about 19.635. So to get the area that I want, I do square minus circle. So if I did 25 minus 19.635, the area that I'm looking for is 5.365. This is my favorable outcome. This is what I want to happen. So 5.365 over the total area, well, that's the area of the square, so it would go over 25. This is the probability that I land somewhere in the shaded region. Our next example, we've got a triangle inscribed inside of a square. Now a point T in the square is selected at random. They want to know where the probability that it lies in the shaded region. So we're looking for is everything outside of the triangle but inside of the square. So once again, if we find the area of the square, side length of 5, 5 squared is 25. If I find the area of the triangle, well, the bottom is 5, the height is the same as the side of the square, so it's 5 and 5. So I take a half times the base times the height, giving me an area of 12 and a half. So to find my total area that I want, I take area of the square minus the area of a triangle, and I get 12 and a half. So this is my favorable outcome. So I've got 12 and a half on the top. Total of what could happen goes on the bottom, which is 25, and I can simplify this down to a 1/2. So half of the time, that point chosen at random is going to land in the shaded region. Our final example for 10.8. Suppose a dart lands randomly on this target. What is the probability that the dart will land in the shaded region? Well, what I'm going to do is I'm going to break these circles up. So I'm going to have the largest circle here with a radius of 8, the smaller circle with a radius of 4, and the smallest circle with a radius of 2. And I'm going to find the area of all of those shapes. Okay, so the radius of 8, I would do pi times 8 squared, which would give me about 200.96. For the circle with a radius of 4, I would do pi times 4 squared, which would get me an area of about 50.24. And finally, the circle with the radius of 2, I would get an area of about 12.56. Now this biggest circle, this is my total area that could possibly happen. So that's going to go on the bottom of my fraction. Okay. Now how I'm going to get what could happen, if you'll notice here, the shaded region is the circle with the radius of 4 without the circle with the radius of 2 in it. So I'm going to take these two and I'm going to subtract them. And if I do that, if I take 50.24 and I subtract from it 12.56, I get the favorable area of 37.6. 0.68, and that's going to be what I want to happen. Now, once I have this, I can leave it as a fraction, or I can write it as a percentage. Now, we haven't done this in previous examples, but just to show you here, if I type this equation into my, or this fraction into my calculator, I get 0.1875. And what I can do with that, to write it as a percent, I take this decimal point and I move it to the right 2 spots, which would turn it into 18.75%. That is the probability that if a dart is thrown at this target, it will land somewhere in that shaded region.